So hello everyone, welcome back to Hasvora Education. Today we will be solving the May-June 2025 paper of the Chemistry 9701, paper 3 variant 3 of the practical. So the time allowed for this paper is 2 hours and the total marks for this paper are 40. So what I will be doing in this paper is that I will take some made up values, or you can say made up values, so to solve all of the questions and to solve, you can say, perform the calculations, because in the end I'm not doing the experiment. I'm just showing you that how you are going to be performing the calculations in your paper, and you are going to be making the tables in a presentable manner. Okay, so that's why I'll be not doing the last question, because it is purely based on the observations. So I'll be attempting the first two questions and I'll be showing you that how to answer the questions that it get you full marks. Okay, so let's move on to question number 1. So this is from the quantitative analysis. So read through the whole method before starting acting practical work. So work appropriate, prepare a table for your results in the space provided, show the precision of the apparatus. So precision of the apparatus means that, for example, if an electronic balance gives you the value to 2 decimal places, so you are gonna record it to 2 decimal places. For example, if I have a mass of 0.67, okay, so I'm gonna or you can say 0.6, okay, so I'm gonna record it to 2 decimal places, like for example 0.60, okay. So that is how you are going to be showing the precision. And in the example of the burette, so if you have a reading of 32 centimeter cube, so you should know that the burette gives you accurate reading to 2 decimal places, so you should write 32.00. okay, so that's how you show the precision of the apparatus. So show your working and appropriate significant figures in the answer to each step of your calculations. Okay, so now let's begin with the first question. Hydrogen peroxide reacts rapidly with acidified potassium permanganate. Okay, so we are reacting the hydrogen peroxide with potassium permanganate. So they have given you this formula. You are going to be using these ratios, okay, in your paper. So Fa1 is the aqueous hydrogen peroxide. Fa1 is the hydrogen peroxide. Then Fa2 is your 0.03 mole per dm potassium permanganate. They have given you the concentration. And Fa3 is 1 mole per dm sulfuric acid. Okay, now what we are going to be doing is that we are going to be diluting the Fa1. This is the method. Okay, so pipette 25 cm cube of Fa1. Now you should keep all of this scheme of work in your mind, okay, that what you are doing. So we are actually performing a dilution. So this Fa1 is actually your original solution. This is your original solution of hydrogen peroxide, okay, and you are taking 25 cm cube of this original solution and you are moving it to 250 cm cube of volumetric flask, and then add distilled water to make up to that mark of 250 cm cube of solution. So what you are doing is that you are moving 25 cm cube of the original solution of the hydrogen peroxide and you are making up, you are adding water to it, you are actually diluting that, okay. So remember the moles that are mole in the 25 cm cube of the original solution are going to be the same as the mole in the 250 cm cube dilute solution. Okay, so just keep this in mind. So shake the flask thoroughly, label this diluted solution of hydrogen peroxide Fa4. So now the name of this diluted solution is Fa4. Let me just correct this a little bit so that you can clearly read this. This is dilute solution. Okay, so this is dilute and then we have solution. And the name of this is Fa4. Okay, so label this dilute solution okay, Fa4, and then we have to perform the titration. Fill the burette with Fa2. So Fa2 was actually your KMnO4, your potassium permanganate, okay, and rinse the 25 cm cube pipette and distilled water and then with Fa4. So we have to rinse it with the water and then we have to rinse it with the dilute solution of the hydrogen peroxide, because we are going to be adding it, okay. use 25 cm cube measuring cylinder to add 10 cm cube of Fa3. So what was Fa3? Fa3 was your sulfuric acid. Okay, it is your sulfuric acid. So we are going to be moving 10 cm cube of Fa3 into the conical flask, and we have actually filled the burette with the Fa2 KMnO4, and we have pipetted 25 cm cube of Fa4 into the conical flask as well. So now many of the students will ask that what is the purpose of your H2SO4 here. Okay, so whenever the reaction between KMnO4 and anything occurs, the H2SO4 actually makes the role of, as you can say, it makes the result more clear, it makes the color change more clear. Okay, so this is just for your aid, the examiner just adds this for your aid. Okay, this makes color change more evident. Okay, because it ensures complete oxidation. Then perform a rough titration of and record your burette readings in the space below. Okay, so now we have to take some made up values. Okay, for example, if I take about you can say 28.50. okay, so remember, if I have a reading of 28.5, then I told you that you have to show the precision of your instrument. For example, if I note the initial reading as 0, so it will be 0.00, because here I am showing the precision of the instrument. Okay, so the rough titre is going to be 28.50. Carry out as many accurate titrations as you think is necessary to obtain consistent results. Make sure you record results, show the precision of your practical work, and record in a suitable form in the space for results all your burette readings and the volume of Fa2 added in each accurate titration. Now also remember that whenever you are going to be performing the experiments, you should have two concordant results. Okay, so what do I mean by concordant results? Concordant results are that results which have, you can say, a difference of 0.1. okay, for example, if I have the rough titre of, for example, if I'm taking up the values, okay, so for example, if I have one reading at 27.50, then the other should be 27.60. okay, so now these two are actually concordant results. But in the case if I have no concordant result, for example, if I have 27.50 and the other is 27. For example 80, okay, so then what I'm going to be doing is that I can just make up this value. Okay, I can just make up it the concordant results. So what I can do is that I can just amend a little bit readings and I can just make this concordant, okay, like this. So that is how you are going to be taking that values, you are going to be taking the average of that values that are concordant. Okay, so now we will make a table here and we will take the values. So first of all, this will be your table. Okay, this will be your table. Then let's add the first column to it. This is going to be the column in which you are going to be mentioning that what are your readings. Okay, and the you can say the name of the readings. For example, the initial reading, the final reading. Okay, and then we will have, this is going to be the number line in which we are going to be writing the number of the experiment. Okay, and then we will just take up 3 additional experiments to the rough title, but you can just include the rough title in this table and you can just take up 3. Okay, so 3, not less than 3, and you can take 4. Okay, so but not less than 3. So let's make another line. This will be your other line, and let's also take one more line. Okay, and now let's divide this. So this will be your final reading, because final minus initial will actually give us the value of the volume used, the volume of Fa2 used, and then this is going to be for your initial reading. Okay, then this one is going to be your volume used, and the last one is going to be the best title. Okay, let's do it like this. Okay, so let me just adjust this a little bit. Okay, so perfect. Now this is very good. Okay, so this is going to be your first experiment, this is going to be your second experiment, this is going to be your third experiment. Then let's just zoom in. This is going to be your final burette reading, and then the unit is going to be centimeter cube. Then this is going to be your initial burette reading, and the unit is going to be centimeter cube, and it is necessary to mention the unit. Okay, and then the volume of Fa2 used, this is also going to be centimeter cube, and then we will have the best Titre, and that is going to be the concordant results. Okay, and we will have, let me just adjust this a little bit, and we will have a tick here. Okay, so for example, if I have the final burette reading of, for example, let's take it as 20, because the first one that we just did in the rough Titre, it was just rough. Okay, so for example, if this is 27.90, this will be 0.00, and I told you that you have to mention the precision, so this will be 27.90. and then let's take the other reading. Let's take this as 3.20, the initial one, and let's just make up a value so that it is close to 27.90. so 27 point plus 3.20, so it will be 31.20, and this will be 28.00. okay, so we have a difference of 0.1, so it will be concordant. Okay, now let's take this value as again as 0.00 in the case if you have refilled the burette, and then we will take this value as 28.2. okay, so now we have a difference of more than one decimal place, so that is not the concordant result. Okay, so this is going to be your best Titre. Okay, or you can say the concordant results. Then B part says, from your accurate titration results, calculate a suitable mean value. Mean value means your average value to use in your calculation. Show clearly how you obtain the mean value. Okay, so 25 centimeter cube of Fa4, the Fa4 was actually your diluted, this was your diluted hydrogen peroxide. Okay, so it required about the mean, so mean will be 27.90 plus 28.00 divided by 2, so the mean will be 27.95 centimeter cube. Okay, and this is the mean value of the Fa2 that was required. Now they are telling you give your answers in the C2, C3, C4 to appropriate number of significant figures. Okay, so you have to calculate the moles of the magnate ions. Okay, so we have to calculate the moles of the magnate MnO4 minus 1 ions. So how we are going to be doing is that we know that KMnO4, if KMnO4 just disassociates, so if KMnO4 just dissociates, it will be MnO4 minus 1 and K plus 1. So we have a 1 to 1 ratio in the ions. Okay, so we can just take the moles of this. Okay, so it will be concentration into the volume. So concentration was given to us. Let's check what the concentration was. It was 0.03. so 0.03 into the volume will be 27.95, the mean. Okay, you are going to be using the mean, and then divide by 1000, because the concentration is in the dm. Okay, so let's calculate this. 0.03 into 27.95 divided by 1000, it will be 8.39 into 10 power minus 6 minus 7 minus 8. Okay, so it will be 8.39 into 10 power minus 4. Okay, it was actually 8.385, but I just wrote it to 3 significant figures. Okay, or you can also write it as 8.385 because we have also taken the values of the mean or any other values to 4 significant figures. Okay, so you can just write it to 4 significant figures. Okay, so it will be 8.385 into 10 power minus 4 moles of MnO4. Now calculate the amount in mole of hydrogen peroxide in 25 cm cube of Fa4. So we have to calculate now the moles of the hydrogen peroxide in the volume of 25 cm cube. So you know that 25 cm cube of Fa4 actually reacted with the 27.95 you can say moles. Okay, so what we are going to be doing is that we are going to be checking the ratio of them. Okay, so the ratio of hydrogen peroxide to manganate ions is 5:2, so we are just going to be doing it like that. Okay, so hydrogen peroxide ratio to the manganate ions ratio, it is 5:2, so the manganate ions are 8.385 into 10 power minus 4, and this is going to be x. Okay, so x is going to be 8.385 into 10 power minus 4 and divide by into 5 and then divide by, it is going to be 2. Okay, so x is going to be 8.385 into 10 power minus 4 and into 5 divided by 2, it will be 2.096 into 10 power minus 3. Okay, so 2.096 into 10 power minus 3. Okay, now calculate the concentration. Now this is the most important part. Okay, this is the most important part in which the student actually gets stuck. Okay, so now let's just try to re-emphasize on the point that what we actually did in this whole experiment. So I told you that we had an original solution of the hydrogen peroxide. Okay, and then we took 25 cm cube, we diluted it to 250 cm cube. Okay, we diluted it to 250 cm cube, and then out of that 250 cm cube we took the 25 cm cube of the diluted solution, which we called the Fa4. Now they are asking us the concentration of the hydrogen peroxide in Fa1. So this Fa1 was actually your original solution. Now how we are going to be doing is that we know the 25 cm cube of Fa4 contained 2.096 to 10 power minus 3 moles. Okay, so the 25 cm cube of Fa4, which was a dilute solution, contained 2.096 into 10 power minus 3 moles. Okay, so how much will the 250 contain, which was the diluted solution Fa4? Because of that we took the 25 cm cube, so it will be x, and let's calculate what the x will be. So it will be 2.096 into 10 power minus 3 into 250 and divided by 25, it will be 2.096 into 10 power minus 2. Okay, so this will be the number of moles in the 250 cm cube. Now remember this 250 cm cube of the diluted solution was made out of 25 cm cube of the original Fa1. Now this means that I told you the number of moles will be the same, okay, in these two, okay, it will be the same in the number of moles will be same in these two, okay. So if we know that 25 cm cube of the Fa1, if we know that 25 cm cube of Fa1 contain 2.096 into 10 power minus 2 moles, so how much will 1000 cm cube contain? Let's calculate this. So it will be 2.096 into 10 power minus 2 into 1000 and divided by 25. So it is 0.8384 moles. And now you can just simply write it as concentration, okay. So 1000 centimeter cube means dm, 1 dm, so you can just simply write it as 0.838 and mole per dm cube, okay. So this will be actually your answer, and this is the part in which most of the students confuse. But once you understand the logic, you can do any question related to this, okay. You can do any question, okay. Let's move on to the D part. So a student suggests that experiment would be more accurate if a 10 centimeter cube of pipette is used to measure Fa3 in place of measuring cylinder. Now this type of question is mostly done in two ways, okay. This is done in two ways. The first way is the precision. You talk about the precision. You talk that the pipette has a precision of measuring to 0.06 cm cube, while the measuring cylinder has a precision of measuring to 0.05 cm cube. Now what actually happens is that we measure 2 times in the measuring cylinder, so the percentage error will be multiplied by 2. This 0.05 will be multiplied by 2. So this means there is more error. There is 0.1 cm cube error in the measuring cylinder, while we only measure once in the pipette, so it will be 0.06. Okay, but what is the case here? What is the case here? Now the Fa3 was actually your sulfuric acid. It was H2SO4. Now you also have to check the second method, which is that in the case if the thing is in excess, then you do not have to worry for the accuracy, okay. So let's check how much of the moles of H2SO4 was needed for this whole reaction. So if we take the amount of MnO4, so it was 8.385 in 10 power minus 4, okay. So it was you can check the ratio, okay. It is 6 to 2, okay. So it was 6 to 2, and we have the moles 8.385 in 10 power minus 4, okay. So you can just calculate this, the required moles. The required moles of H plus ion, it was, so we have the ratio of H ions to the KMnO4 ions. It will be 8.385 into 10 power minus 4, and this will be X. So X will actually be equal to 8.385 into 10 power minus 4 into 6 divided by 2. This will be equal to 0.002 moles, okay. So these were actually the required moles of H plus ions for this particular reaction, okay. These were the required moles for this particular reaction. Now let's see that how much ions they provided us, okay. So we are taking 10 cm cube. You must remember that we took 10 cm cube of the Fa3. Remember we took the 10 cm cube of the Fa3 into the conical flask, and then we also added the you can say the KMnO4, okay. So we took 10 cm cube, so it will be 10 cm cube. And what was the concentration? Let's check the concentration as well. So concentration was 1 mole per dm, okay, of the H2SO4. So if we just calculate the moles, what was the moles? So it will be 10 cm cube into 1 mole per dm. You can just divide this by 1000, so it also converts to dm. So this will be 0.01, okay. So the number of moles that are being provided are more actually more than what we require, okay. So this means that the H plus ions are in excess, the H plus ions are in aqueous, so the accuracy of the instrument doesn't matter. Okay, because we are adding that in excess. Okay, so for example, if you just do not measure it, okay, you just add it, so that's the point. Okay, so that is in excess, so the accuracy will not matter. Okay, it will not affect your calculations. So that was the answer for this. So you also always should check the both of the methods. In the case if it is not in excess, then you will go for the first method, which is talking about the precision, of the instrument. Okay, so let's move on to question number 2. So you will now determine the concentration of a solution of hydrogen peroxide by a different method. Hydrogen peroxide decomposes slowly into water and oxygen at room temperature. So they have told you that hydrogen peroxide actually decomposes into the water and the oxygen at room temperature. This reaction is exothermic. What does exothermic means? That it releases energy. Okay, the enthalpy change will be negative. When a catalyst is added, the decomposition is fast and there is a measurable temperature rise. Okay, now Fa1 is they have given you this reaction for 1 mole of hydrogen peroxide, and they've also given you the delta H change. Okay, so this will be beneficial when we are looking for the you can say the amount of the hydrogen peroxide that we will be reacting, so we can just compare it to that. Okay, so if the 1 mole of hydrogen peroxide releases this much energy, then we can check that how much over energy changes. Okay, then they have given you Fa1 is the aqueous hydrogen peroxide. Okay, and Fa5 is the manganese oxide. So manganese oxide. Okay, so manganese oxide is the catalyst here. Then the method for the experiment 1, this is your experiment 1. The results for this are going to be noted as well, and also for the experiment 2. So support one of the cups in the 250 cm cube beaker. Use 50 cm cube measuring cylinder to add 25 cm cube of Fa1 into the cup. Place the thermometer in the Fa1 and tilt the cup if necessary, so that the bulb of the thermometer is fully covered. So what you are going to be doing is, first you will add the 25 cm cube of Fa1. Okay, and you know that Fa1 is the hydrogen peroxide, it will decompose. But why are we adding Fa5? Because it is a catalyst and it will speed up the process, because if you try to wait for it, it is not going to happen like that. Okay, so first of all, you add 25 cm cube of Fa1, the hydrogen peroxide. You are gonna place the thermometer, you are gonna measure the initial reading, the initial temperature, and then you are going to be adding the heaped spatula. Heat means full spatula measure of Fa5, the manganese oxide, into the solution in the cup. Okay, stir constantly until the maximum temperature is reached. So record this temperature. So what you are going to be doing is that then you will stir the container until all of that mixes, and manganese oxide is a type of black solid, so until all of the black solid mixes up and dissolves. Okay, and then you are going to be recording the highest temperature it reaches up. Okay, then you are going to calculate and record that temperature rise, and rinse and dry the thermometer. So what are the things that we are going to be noting down in this type of experiment? First thing is your volume of Fa1. Okay, then the initial temperature. Okay, I'm just giving you a rough idea. Then the final temperature, and then the temperature change. Okay, delta temperature. So these are going to be the things that you are going to be noting down according to each experiment. Then the experiment 2 is support the second cup in 250 cm cube of the beaker, and then use 50 cm cube of the main cylinder to add 40. Now this time we are adding 40 cm cube of Fa1. Okay, to the second cup. Measure and record the initial temperature, the same thing. Okay, and then we are going to be adding the Fa5. And remember, in this type of experiment, usually your Fa5 or your solid actually finishes up, so you can just ask the invigilator to give you more. Okay, and they will give you. Stir constantly constantly until the maximum temperature is reached. Record this temperature, calculate and record this temperature rise. So now what we will doing is that we will just make the table for this. Okay, so we will make the table for this whole experiment. So this will look like, this will be the main table. Okay, so let's just little bit reduce the size. Okay, so then we will have the first row. This will be for the headings. Okay, and what headings we will have? First of all we will have the experiment number. Okay, so whether it is experiment 1 or experiment 2, this will be experiment. Then we will have volume of FA1 used, and it will be in the cm cube. Okay, so always and always take care of the units. You have to add the units. Okay, after that we will have the initial temperature, and it will be in your Celsius. Then you will have the final temperature, and it will be also in Celsius. And let's just increase the size a little bit of this table. Okay, so let me just increase the size of this table. So let's just move it to the little bit to the left. So, and then increase the size a little bit more. Okay, and this line as well. Now the final reading will be temperature change, and it will also be in your Celsius. Now let's make the columns for each of them. So this will be your first column, then this one will be your second column, then your third column, and then your last column. Okay, and let's divide this whole area into two because we have two experiments. Okay, so we are going to be taking some ample space. So now this is going to be your experiment 1, this is going to be your experiment 2. So how much of volume of FA1 we used in the first experiment? It was 25 cm cube. Okay, so, and we use pipette. Okay, so what is the least count of the pipette? You are going to be recording it to 25.0. okay, so 25.0, and this is going to be your 40.0, and then the initial temperature. And remember, whenever you are recording the temperature, so either you are going to be writing it as, for example, if I have a temperature of the room temperature, okay, it is going to be 27, and you are going to be adding 0.0 because the least count of the thermometer is 1 divided by 2, which is 0.05. So you will record it to 1 decimal place, and you can also do it to 27.5, but not the middle values. Okay, you cannot do 27.2, this is wrong, but you can do it to half. Okay, in the case if it is perfectly in the middle of the value. So for example, if I take the initial temperature as room temperature, it is going to be 27.0, and the final temperature, for example, let's take it as, for example, you can say, let's take this temperature change as 38.0, and because we have used more volume in the second experiment, we have used 40 centimeter cube, so let's take it more. Okay, so it will be 45.0, and let's check the temperature change. So 30 minus 27, it will be 11.0 Celsius change, and the second one will be 45 minus 27. Let's calculate what it is. So 45 minus 27 is 18 Celsius. Okay, so this is going to be our table. Okay, now calculate the energy change in joules in experiment 2. Okay, so we have the experiment 2. So the energy change is Q is equals to mc delta T, where m is the mass, c is the specific heat capacity, which is equal to 4.18, and delta T is your temperature change. Now how are we going to be taking the mass? Now you should know that we use the assumption 1 cm cube is equal to 1 gram. Okay, so how much cm cube we have in this experiment? We have 40 cm cube. This means we will have 40 gram. Then what is the specific heat capacity? It is 4.18, and the delta T, the temperature change, is 18. So now let's calculate this. Okay, so 40 into 4.18 into 18, this will be 3009.6 joules. Okay, so 3000, and let's take it, write it as 3010 joules. Okay, so use the information given in your answer to B1 to calculate the concentration in mole per dm of the hydrogen peroxide. Now this is a tricky part as well, because I told you, remember, in the information they are actually giving you the hint as well. Okay, that how we are going to be calculating the concentration. So what they have done is that they have given you the energy change for the 1 mole. Remember, I told you this is for 1 mole of hydrogen peroxide, and this releases 98.2 kilojoule. So if I just use 1 mole of hydrogen peroxide, and this will actually release minus 98.2, and it is kilojoule. Okay, so it is, yes, it is kilojoule, so it will be into 10 power 3 joules. Now if 1 mole of H2O2 releases 98.2 kilojoule, so how much x moles will be releasing 3010 joules. Okay, so do not forget the kilojoule in the first one. So now you can just cross multiply. This is the simple type of question, but most of the students struggle to find out that how we are going to be solving that. Okay, so this will be, let's calculate this, 3009.6 into 1, and then divide this by, let's calculate this now. So this will be equal to 0.03. Okay, so x will be equal to 0.0306 mole. So you can just write it as 3.06 in 3.065. Let's take it to 4 decimal places, so 4 significant figures, and into 10 power minus 2 mole per dm. Okay, so the concentration that we are actually measuring in both of the experiments, the first question and the second question, will be varying, because now we are actually taking the assumption based values. Okay, we are not taking the real experimental values, because in that case it will be similar, it will be close to each other. So this is now the question is finished, and now they are asking you some theory type questions. Okay, so the concentration of the hydrogen peroxide in FA1 calculated using the method given for question 1 is more accurate than using the method given for question number 2. So heat loss is large source of error, and let me tell you that how you can avoid the heat loss in case if it asks you in your exams. Okay, so one way it can be avoided as you can place the lid. Then the second way that can be avoided, you can use the insulation, and the best insulation that I will recommend is the glass wool. Okay, it is glass wool insulation. So this is how you avoid the heat loss, and it is the largest source of error when carry out the method for question number 2. Describe and explain the effect. Now they are asking you the effect. Okay, they are not asking you how you're going to be reducing it. So what is the effect of heat loss on the value of concentration of hydrogen peroxide calculated? Now just think of it like in the way. Okay, so if 1 mole is actually releasing 98.2 into 10 power 3 joules. Okay, so we also know that 1 mole releases this much energy. Okay, so what will happen because of the heat loss? Because of the heat loss, there will be less temperature change, and because of the less temperature change in the formula of the MC delta T, there will be less delta T. This means we will have less energy, or you can say the enthalpy change, and because of the less enthalpy change, we will get less number of moles. So for example, if I have 3010 joules here, so for example, if I have a little temperature and I just the value gives me 2800, so it will be less number of moles. Okay, so this is going to affect the concentration by reducing the number of moles. So heat loss will reduce will reduce the maximum temperature change, giving less energy change. Hence, we get less number of moles of H2O2. So this will be the answer, okay? The second part says a student suggests that calculating the concentration of hydrogen peroxide using the method in question 2 would be less accurate when the concentration is lower. Okay, so what will happen? It will be less accurate when the concentration is lower. So what happens when the concentration is lower? So if you have a lower concentration, so what will happen? There will be less temperature change, and when there is less temperature change and there is heat loss involved, so what will happen? There will be more percentage error, because you already have less temperature change. For example, if I have from 27 Celsius to about you can say 30 Celsius, okay, because there's low concentration. So if I already had very little range of temperature change and we have a heat loss of about, you can say, 1 Celsius, okay, the heat loss actually results in the loss of 1 Celsius temperature. So we will have 1 divided by 3. So 1 divided by delta T, which is the change. So 1 divided by 3 will be into 10 into 100 will be your percentage error, okay. So there will be more percentage error. So in the case if you have a larger range, for example, if I have a change of, if I have more concentration, there will be more delta change. And for example, if I have a change of 20 Celsius, okay, so then this percentage error will be significantly reduced. There will be less percentage error, okay. So this is the main concept. So lower concentration results in less temperature change, hence heat loss will add more percentage error to it. And in the start you are going to be writing that yes, the student is correct, okay. So this will be your answer for this question, and we have successfully completed the question number 1 and question number 2. We will not be doing the question number 3 because that is purely based on the observations, and I have told you how you're going to be performing these calculations, and you're going to be making the tables, okay. And in the case if you want this paper, what you can do is that simply you can just go to my channel, okay, and then you will go into the links. Once you get into the links, you can just click here on my website, okay, and then in the website you will navigate to the section, this section of the past paper, okay, of the A levels. And then once you get into the A level section, then you will actually see the recent papers of May-June 2025, okay, of the May-June 2025. And once you get into the May-June 2025, you will get all the papers of the maths, your physics, then you have the computer science, your chemistry, and your biology, okay. So in the chemistry section you will get into the 9701 paper 3 May-June 2025, and you will have the papers of it here, okay. So this is how you will get the paper. And this was all for today. If this video was beneficial for you, share with your friends and share this channel with your friends as well, and do subscribe channel. So I'll be meeting you in another video. Till then, take care and goodbye.